wabarakatuh. Today's topic is about Hagen-Poiseuille equation, and basically in this slide I will teach you about the derivation of the Hagen-Poiseuille equation. So this is subject CHE 241. Okay, so the derivation of the Hagen-Poiseuille equation for laminar flow in a straight and circular pipes is based on the following two assumptions. So you can use the Hagen-Poiseuille. Basically, the Hagen-Poiseuille equation is to calculate the delta P. So the pressure difference in a straight pipes, and it must be a laminar flow. So you cannot apply the Hagen-Poiseuille for the turbulent flow. If your equation question have fittings in the pipes, then it is a laminar. Therefore, you cannot use the Hagen-Poiseuille. Why? Because there is a fittings, and the Hagen-Poiseuille only applicable to laminar flow and straight pipes, okay, and circular pipes. And to derive the Hagen-Poiseuille, we have two assumptions. The first one, viscous property of fluid follows Newton's law of viscosity, which means the liquid that flows or the fluid that flows in the pipe or in the circular pipes must follow the Newton's law of viscosity. So as you know, in the chapter 1, we have so many different types of fluid, which is and actually it divided or it categorized into two different types of fluid. One is Newton's law and second is non-Newton's law. So those fluid in the Newton's law of Newtonian fluid can be used Hagen-Poiseuille. So the rest, the non-Newtonian, for example, pseudoplastic, Bingham fluid, rheopactic fluid, and many more, is not under this Hagen-Poiseuille. You cannot use Hagen-Poiseuille, and you can apply the Hagen-Poiseuille to that non-Newtonian fluid. Okay. Second is there is no relative motion between fluid particles and solid boundaries. That is, no slip of fluid particles at the solid boundary. So which means that at the wall of the circular pipes, there is no slip condition phenomena occurs. Okay. So this is the diagram. These diagrams represent the flow of fluid in the pipes. So this hatch is actually represent the pipe's thickness. Okay. So for example, I have a pipe. Okay, pipe. And then I will cut through, and then it will show like this. So we take a small particle here that represent the fluid. So we have P pi r square here. So P pi r square is the unit of force. So this is force 1, because we know that if the fluid flows, there is a pressure here. So P here times with the area of this surface, we will get the force. Okay. Pressure is equal to force over area. So if we rearrange this equation, force equal to pressure times with area. Now we have circular shape. So F equal to P pi r square. Okay, this is force. I denote it as F1, and then we have if we have pressure, for example, somebody push the box at this direction of the force, and there is another force that act to this force. Okay, So which means that if there is a force here, and it will have another force at here. So how to calculate the force here? So we know that this is P, and then this is delta X. Okay, X, delta X is the change of X. So to know what is the pressure here, so, and this is change of pressure over change of X. Pressure will change based on the X. So if you want to find what is the force here, so we will make P, we will wrote P plus del P, change of pressure, over change of X. Pressure will change based on the X, times with the X, okay, dx, and times with the area. So this is the unit, this is the pressure, and then times with the area, so we will get the force. So I denote it as F2. So we know that when the liquid flows in the pipe, we have two axes, okay, X and Y axis. To derive the Hagen-Poiseuille law, we are only considered the X direction, okay, so we will not consider at Y direction. So we only consider the X direction. So F1 is X direction, F2 also X direction. So as we can see here, we know that when the fluid is there is a force here, another force, where this force is a shear force. So to get shear force, we have to times tau with area, okay, and dx, tau 2 pi r dx. So this is a shear force. So shear force, I will denote it as F3, and it will act at this direction. So we have force here, and then another force here for the shear force, and force here is for P plus del P over del X dx by R square. So now we want to derive the equation, okay. So before that, as you can see here, we have Y. Y is the length of the length from pipe wall to center, whereas for the R value, R here, the radius here is from center of the pipe to this circle, based on the circle lah. Okay, this circle, and then that area is from here to the pipe wall lah. So pipe wall here is R, and then from this pipe wall to the center of the pipe is Y. Okay, and we have another terms here, x1 and x2. So x1 is from here, okay, this is 0, and then x1 is to the here, start of the pipe, and then 0 to at the end of the pipe. So this is x2. So if we subtract x2 with x1, we will get the L value, which is the length of the pipe. Okay, now we will derive the equations of the Hagen-Poiseuille law. So we know that there are three force act on that fluid. So we have F1, we have F1, okay, we have F1, and then we have F2, and we have F3. So to for a fluid in a fluid in a static condition, the summations of Fx is equal to 0. So all of this is in x direction. So summations of Fx is equal to 0. So we have to add all of these, okay, and equal to 0. So after that, we have to take a look at the directions of each of the F. So we take a look at the F1. So the directions of the P of this force is in this direction. So I change the color to red. So we have this first one, F1 is the direction at this. Okay, so therefore, when the direction is like this is a positive value. Okay, so for the F2, we have the directions to this, like this. Okay, and this direction is a negative direction. Same goes to F3, where we have these kinds of direction, and then this is negative direction. So we have put the directions of this F, and then we already identified negative or positive value. So F1 is a positive value, F2 is a negative value, F3 is a negative value. So we have to change here. So F1 is a positive value. Okay, plus we have F2 is a negative value, F2 plus we have F3 negative, F3. So equal to 0. So therefore we have F1 minus F2 minus F3 equal to 0. So we know that F1 is P by R square. For F2, we have P plus del P over del X dx, okay, and pi R square. And the last one, we have F3 equal to tau 2 pi R dx. Okay, so we substitute all of this information into this equation. Okay, so P pi R square minus P plus del P over del X dx, okay, pi R square minus tau 2 pi R dx equal to 0. So we have to simplify this equation, rearrange the equation and simplify. So we will get the equation becomes tau equal to negative del P over del X R over 2. So you have to simplify this equation, rearrange it, and to get tau is equal to what? Okay, now I already simplify it, and we get that tau equal to negative del P over del X. So from here, we know that if we substitute the value of R, okay, R equal to 0, we will get that the shear force, okay, or stress is 0 at the center of the pipes. So R0 is center of the pipe. So the R will start 0, will start from center to pipe wall. Therefore, center of the pipe will be R equal to 0. So if we substitute the R value inside this equation, we will get that the shear force or shear stress stress is 0 at the center of the pipe. Whereas if we substitute the R equal to R naught, we will get that tau is at maximum value. Tau is at maximum value when R is equal to R naught. So R naught here is the is from center to the pipe wall. That is R naught. Here is R naught here. So R naught is from the center to the pipe wall. So we know that from the Newton's law of viscosity, I put it NLV, Newton's law of viscosity, we know that the tau is equal to mu du over dy. But now we want to change dy. So as we can see here, as the y increases, r will be decreases. Okay, for example, okay, let's say we want to know that this is the first, this is r, this is y, and then as the y increases, r will be decreases. Okay, so as the y increases, r will be decreases. From this, we can substitute, okay, we can substitute dy, okay, as y increases, r will be decreases. Therefore, dy equal to negative dr. So substitute this into this equation. Okay, it will become tau equal to mu du over dy. Oh, sorry, du over negative dr. So you will get that negative mu du over dr. Okay, so that is the value of tau, that equation of tau. So now I put it here as 1, and this is 2. So next, what we have to do is substituting 2 into 1. We substitute because here we have tau. Now tau here is negative mu du over dy. So we substitute this equation into 1. Okay, we will get that negative mu del u over del r. I'm so sorry because this is not du, it is del. Okay, del u over del r. Okay, negative mu del u over del r equal to negative del p over del x r over 2. Okay, or we can rearrange this equation and it will become del u 1 over 2 mu del p over del x, okay, comes with r dr. So we have this equation, and then what we have to do is we have to integrate. Okay, integrate. So integrate this one from 0 to u, and then the integration at this side is integrate. Okay, so what we get here when we integrate, we will get u equal to 1 over 4 mu del p over del x r square plus c. Because we do not have limit here, therefore we have to put a constant when we integrate this equation. So now what we have to do is we have to determine what is the constant of this equation. So how to know and how to get the value of c, we have to substitute the value which we already know that the value is 0 or the value is how much. So you already know that the value of that terms or that parameters. So you can substitute into this equation. Now what we know from this equation, from this figure, as we can see here, at this point, okay, on the surface of the pipe surface, we know that before this is no slip condition. No slip condition, u is equal to 0. So as we can see here, when here is the velocity at wall of the at the pipe wall is equal to 0, therefore the radius of this pipe is r naught. So we will substitute u will be 0 at r equal to r naught. So from this, we substitute u 0, u is equal to 0 at r equal to r naught. So when we substitute that value, we will get the equation for C is negative del P over del X R naught square over 4 mu. So that is our constant, and substitute our constant into this equation. So to get the equations of u. So u that we get is equal to 1 over 4 mu, okay, negative del P over del X R naught square minus R square. Okay, this is the equation number 3. Okay, this equation, as we can see here, it is a parabolic equation. Okay, parabolic equation. So we know that when the when the liquid flows in the pipe, it will behave, for the velocity profile, it will behave as a parabolic equation. Okay, so every one of these line represent the velocity, the fluid particles, and then this one is velocity. So velocity will form a parabolic shape, okay, in the pipes. So this is pipe, okay, and it will form a parabolic shape, okay, and this is parabolic equation. So from the equation, we can actually calculate what is maximum velocity, because we know that at the center of the pipe, based on here, we know that at the center of the pipe here, if we draw here, at the center of the pipe, this is center, u is maximum. So how to find, or is there any equation that can find the maximum velocity? Yes, you may use this equation number 3, and then you have to substitute the condition at that point. So u is a maximum when r is 0. So now after we substitute that condition, we will get that u maximum is actually equal to 1 over 4 mu, okay, negative del P over del X R naught square. So it is from here. So if you substitute R equal to 0, then 0 to the power of 2, it will be 0. Then u is maximum, u max. Okay, you will get this equation. So this condition, you have to substitute into equation 3, then you will get this u maximum. Okay, so equation 3, this equation, and combining with this equation, okay, u maximum, you can find that, you can as you can see here, 1 over 4 mu negative del p over del x r naught square. So here is the same. Okay, you can actually substitute this equation into equation 3. So after you substitute, okay, I put it as a 4 into 3, and then you simplify. So you will get that U equation is actually U maximum 1 minus R over R naught square. Okay. If you already know about the maximum velocity, then you may use this equation in order for you to determine what is the value of U. Okay. Now, volumetric flow rate, because our concern is volumetric flow rate in the pipes, we can actually calculate the volumetric flow rate by using the equations of, okay, dq equal to u dA. Okay, so now we already know about the u equation for u, so we do not use this equation to substitute into this equation. So we will use equation number 3. Okay, and we substitute into this equation. So dq equal to 1 over 4 mu, okay, negative del p over del x r naught square minus r square. This is the equation. And then dA is 2 pi r dr. So now what we have to do, we have to integrate this equation. For the q, we will integrate from 0 to q. And then for this side, we have to integrate from r to from 0 to r naught. Okay, 2 pi r dr. Okay, after we integrate, we will get that q equal to pi over 2 mu negative del p over del x, and then 0 to r naught this is not the product of derivation, integration. I already integrate at this side first, so we will get q, but this side I'm not yet integrated. So if I integrate this, I will get, after that, after I simplify, I will get that q equal to pi over 8 mu negative del p over del x r naught square. Okay, this is the equation to find what is q. So to get what is the average velocity, so average velocity, so we know that the average velocity is v equal to q over a. So this equation comes from q equal to ua, or u, normally u or v. Okay, both of these are the same, okay, for the fluid mechanics. So then we substitute the q value and a q equation and then a equation. So we will get that 1 over 8 mu negative del p over del x r naught square. This is equation number 5. Okay, so you have to compare this equation with the u maximum equation 5 to 4. Okay, oh, I'm so sorry, I make it double, which means this 4. So you have to compare 5 and u maximum, u which have u maximum in that equation. So what you have to do is you compare, and then when you compare, you will get that compare equation 5 with 4. So you know that when you substitute that equation, you will get that u is actually u maximum divided by 2 for this flow. Okay, to find average velocity, you can divide u maximum by 2. Okay, now equation 5 can be rearranged into, so we want to rearrange this equation, and we want to change the delta p over del x into p over x. So what we have to do, we have to rearrange the equation. From this equation, we rearrange, so we will get that negative del p equal to 8 mu v over r naught square del dx or del x. Okay, del x. So then integrate with respect to x. Okay, so x1 and x2. So from here we know we have x1 and x2. So therefore we will integrate this equation from x1 to x2, and then L, as I mentioned before, to get L we have to subtract x2 with x1, so you will get the length of the pipe. So from here, the length of pipe is x2 minus x1. So we integrate this equation. Okay, integrations of p1 to p2, so del p, okay, negative del p, then we have 8 mu v over r naught square, equations of x1 to x2, and then d del x. So after since d equal to, okay, since d equal to 2r naught, so to find diameter of the pipe, okay, the diameter of the pipe is 2r naught, so we get this diameter. Okay, so d equal to 2r naught, therefore p1 minus p2 equal to 8 mu VL over R naught square. Okay, so here we will get, if we change R naught to diameter, so we will get that 32 mu VL over D square. So this is when you use velocity. Okay, we can change this equation into Q. So Q is VA. So velocity is Q over area. So area is pi d squared over 4. So Q over pi d squared over 4. So from here we know that V is 4Q over pi d squared. This equation you have to substitute into this equation. So V terms here change into this equation. So substitute with this equation. So what you have after you substitute into this equation, you will get that delta P is equivalent to 1 to 8 mu Q L over pi d to the power of 4. So both of this equation is Hagen-Poiseuille equation, and you must remember that the Hagen-Poiseuille only can be applied to laminar and straight pipe. Okay, straight pipe with no fittings. Okay, which means no fittings can be allowable if you apply Hagen-Poiseuille equation. So remember, laminar and straight pipes. So first, when you do the question, you have to calculate what is the Reynolds number, and from the Reynolds number, you can actually determine whether that is laminar, transition, or turbulent flow. So after you get the Reynolds number, you have to determine either that pipe is a straight pipe or that pipes have some fittings into its arrangement. If there is some fittings into the arrangement or pumps or whatever fittings in that pipe, so you cannot apply the Hagen-Poiseuille. At that point, you have to apply the Bernoulli's equation, where I will teach you after this video, how to use Bernoulli's equation to determine what is the delta P, pressure drop inside of the system, okay, of the piping system. If you have fittings and you have pumps, then we will go to the chapter 9. If you have fittings, and then the major losses comes from the straight pipes, and you will use that Bernoulli's equation. Okay, the case that Bernoulli's equation can be applicable for laminar and turbulent flow. Now for the Hagen-Poiseuille is only for laminar and straight pipes, circular pipes. Okay, straight and circular pipes. Okay, thank you. That's all for